In this final video on transformations, we're going to be talking about non-rigid transformations. So to begin with, so far we have covered shifts and reflections, which are rigid transformations. And they're called this because they do not change the shape of the graph. Before moving on to non-rigid transformations, however, which actually distort the shape of the graph, here are a few pro tips I wanted to provide for helping transform graphs in general. So the first pro tip is that inside horizontal, in the word sort of inside always means that it's going to be some sort of a horizontal transformation. And this always means that it affects x only. Namely, we saw at the end of the last video that this has some effect just on the domain. Conversely, outside, if it's outside of the function, the transformation happens sort of on the outside, then it's a vertical transformation and it's only going to affect the y values. Namely, the range gets affected. So that's the first pro tip. The second pro tip is that the inside acts kind of backwards. Namely, you'd expect that adding c would shift it probably to the right, but it actually shifts it to the left. Similarly, when we subtract c on the inside, it shifts it to the right and not the left. So it's a little bit backwards on the inside. Finally, order of operations actually really does matter here. Why is that? Well, the reason why order of operations matters is essentially it matters in terms of, do we reflect first or do we sort of shift first? And as we'll see later, do we sort of scale first as well, okay? And so because of that, it really does matter. And we saw an example at the end of the last video where that came into play. So for another example, let's look at a transformation of the square root of x. So this transformation is 3 minus square root of x plus 2. If you look at this, this is really, you can think of this as 3. If you have g of x equal to the square root of x, this function would be f of x is 3 minus g of x minus 2. Rewriting that around, that's negative g of x minus 2 plus 3. Now, horizontally, what's happening? Horizontally, all we're doing here is subtracting 2, which means we shift it to the right by 2. So, right 2. However, if we look at vertically, what's happening? Vertically, we have that we first sort of, we have a vertical reflection, so to speak, but the vertical reflection is really, it flips it across the x-axis. So, reflect, you reflect vertically, and then you also add 3, so, and then you shift up 3. Again, the negative applies first here, then you add the 3. So, first we shift to the right 2, and vertical and horizontal can go either direction. You don't need to, you can do all your horizontal transformations first, then your vertical ones, or your vertical transformations, then your horizontal. It doesn't matter because horizontal and vertical are separate from each other, okay? Vertically, so let's do the horizontal first. Horizontally, we shift to the right by 2, then we reflect and shift up by 3. So that's where this point ends up, and so because of the reflection, we actually end, this gets down here, and so we end up with this graph. Okay, so this is our new reflected graph. Now that we've worked an example of that, let's go ahead and talk about stretching and compressing, which are non-rigid transformations, as they're going to distort the shape of the original parent function's graph a little bit. Namely, we're going to stretch it or possibly compress it, which the book calls shrinking. So, let's talk about the vertical stretching and compressing. For the graph of y equals f of x and a positive number c greater than 0, we have that c times f of x is, it's a vertical stretch when c is greater than 1, and it's going to be a vertical shrink when c is less than 1, is between 0 and 1. So for example, let's compare the graphs of each of the following functions with the graph of f of x equals absolute value of x. Well, here we see that this is really 3 times f of x. And over here, similarly, this is 1/3 times f of x. What that means is this is going to stretch vertically. So vertical stretch by a factor of 3. What does that mean? Well, it means each of your y values here get multiplied by 3. So 0 still becomes 0, but then 1, what was at 1, now gets bumped up to 3. What was at 2 now gets bumped up to 6. What was at 3 gets bumped up to 9. And then similarly over here. So as you can see from this, it really does stretch the graph. Okay? And so it's sort of like we're taking this graph and we're stretching it up by this factor of 3. Here we expect that it'll actually shrink or compress down. So how does that happen? Well, 1/3 times x, so that would be a vertical shrink by a factor of 3. But how does it do that? Well, it takes 1 and now it goes to 1/3. It takes 2 and goes to 2/3, which is about here. It takes 3 and gets sent to 1. And then similarly over here. So it just takes those values, those y values, and divides them by 3. Sorry, move that all around. Okay? Now it's time for you to try an example, so go ahead and compare the following 2 graphs to the graph of x squared. So I graphed x squared here, and go ahead and try graphing g of x equal 4x squared and h of x equal 1/4 x squared. On the count of 3, I'll reveal the solution. 1, 2, 3. So here we see that here we're vertically stretching by a factor of 4, so it stretches the graph up, namely the points at 1 and -1 get moved up, get multiplied by 4 up, where 0 stays the same. Here, however, we shrink vertically by a factor of 4. So this point got brought down, this point got brought down, this point got brought down, and this point got brought down. All right, moving on, horizontal shrinking and stretching. So for the graph of y equal f of x and a positive number c greater than 0, f of cx is a horizontal shrink when c is greater than 1 and a horizontal stretch when c is between 0 and 1. Again, here we have sort of something happening on the inside, which means it's really horizontally happening. And it's backwards in the sense that before, vertically if we did c greater than 1, it created a stretch, but now horizontally it creates a shrink, and vice versa for shrinking and stretching for when c is between 0 and 1. For example, let's compare the graph of each of the following functions with the graph of f of x equals 2 minus x cubed. So f times 2x, f of 2x, what this does is this says, oh, well, we're going to go ahead and this would be a horizontal, which one? So here c is greater than 1, so it's a horizontal shrink by a factor of 2. A factor of 2, which means all of the values, all the x values get halved. So this gets sent to 1/2 of itself. That also gets sent to 1/2 of itself. And so what we have here is we've made this graph even thinner in a sense. Okay. Over here, however, it's going to enlarge the graph because this is a horizontal stretch by a factor of 2. Stretch by a factor of 2. So what does that mean? What that means is we're actually stretching it. So 1 gets sent out to 2. This 1 gets sent out to 2. 0 stays put. And so what we have is we get something like this. This really spread out function. And now, once again, it's time for you to work an example. So go ahead and compare the following graphs to the function f of x equal x squared plus 3. On the count of 3, I'll reveal the answer. 1, 2, 3. So here we see that this is a horizontal shrinking by a factor of 2. And so 1 gets into 1/2, similarly. 2 gets into 1, and so on. So it pushes in the graph. Here, we're stretching horizontally, which by a factor of 2. So 1 gets into 2, the x value of 2 gets into 4. And so what's doing is essentially stretching out the graph. Let's do one more final pro tip on top of this. So adding and subtracting means shifting, but multiplying means scaling and reflecting. It's only a reflection, of course, if there's a negative in there. So for example, let's try graphing this function. Well, the first thing to note here is identify what the parent function is that you're trying to use. The parent function is f of x equal absolute value of x. What does that look like? Well, that looks like, it's helpful to see it. Like that, and give myself a few points like that. Okay, so that's f of x equals absolute value of x. Now, how are we shifting this? Well, let's again look at the vertical and the horizontal separate. Vertically, as in what's happening on the outside, is there's first, we either scale it by 3 or apply the negative. Let's go ahead and scale the 3 first. So we scale it by 3, which is to say that we stretch by a factor of 3 and then we reflect. Again, that's with respect to the x-axis, in x-axis. And then we shift up 2. So using orb operations, we get that. Horizontally, all we're doing, and that's on the inside of the absolute value, that would be, we're subtracting 1, so shift, because things are backwards on the inside, so not that way, but up, so shift right 2. Shift right by 2. So, let's think about what happens here. Here, first, let's do all the vertical stuff. We're going to stretch by a factor of 3. So we take this point, it gets stretched by 3, it gets reflected, so then that means 1, 2, 3, no, 1, 2, so yeah. It gets moved up to 3, but then it got reflected, so down there. It also, and then it got shifted up by 2. So what's sort of happening here? Well, this whole graph is essentially getting stretched and then shifted up. This is a mess. Let's take a few moments. So, yeah, we can get this to work. Here we have, so shifted down and then moved up by 2. So this point, let's start with 0. The point 0 gets shifted, the stretch doesn't affect it, the reflection doesn't affect it. It's shifted up by 2. And then right by 2 as well. Yeah, right by 2. Yeah, right by 1. Yeah, that's one thing that's messing me up. There, good. Now, what happens? Well, let's take this point. This point gets scaled to 3. Then it gets reflected down to -3. And then it's shifted up by 2. and over 1. Similarly, we can see what happens with this point. With this point, we see that it gets scaled up to 3, reflected, up to over 1. And now you have a good idea of what this graph should look like. Here, you expect now, because of the scaling, that this point will be there, that point will be there, and so on. Because you expect the lines to basically stay the same. So take your time, as I had to as well, and eventually you'll get there. Just go sort of point by point, moving things around. As such, if you want more practice, be sure to see pages 72 through 74 of the textbook. You should be able to do all those problems now. So some are just shifting, some of them are just shifting and reflecting, or just reflecting. But here's sort of the remaining problems of the ones that aren't just those. But anyways, in our next video, we'll be talking about algebraic combinations of functions.